In this example, we're going to look at something called the central limit theorem. Now, the central limit theorem stems from the last section where we have means of sample means and we put them together. What we found is the central limit theorem says that the means of these sample means are going to tend to be normally distributed. And the cool thing is that the samples themselves don't have to be normal. As long as you have a sample size of greater than 30, then the means of your sample means will have that normal distribution. Now, if you start with the fact that your population is normally distributed and you take samples from that population, then your sample size doesn't really matter. You can have a sample size less than 30. But 30 seems to be the magic number that we can use so that it doesn't matter what distribution our population is, the means of those sample means will have a normal distribution. Let me demonstrate to you what I mean by that. Oh my God. Here we go. Now we're in the stat crunch. I'm going to use this applet right here, and I'm going to click on my sampling distributions. And I'm going to start off with a uniform distribution. And my sample size is going to be something I'm going to select next. So what this does is just create a uniform distribution rectangle that we talked about last section. And I'm going to get this graph right here. So here I have my uniform distribution. It's this big flat rectangle. And I have values for my random variables between 0 and 50. I'm going to sample one time. So it's going to make a sample size of 2. So I pick 2 values from this. And then I take the average of these 2 numbers here I have in my middle. And this is my mean of those 2 numbers. I'm going to do another sample. Pick 2 things. So I pick these 2 things, and then that mean is right down in the middle. Now what I'm looking at here is the mean of these 2 values down below. So here, for my samples that I have here in this part, this is the sample, the mean of the sample I just took, and then here is the mean of the sample means. Now what happens is as I do this many times, pick 2, mean, pick 2, I get the mean, I pick 2, and I get the mean. I'm creating a distribution of those sample means that I have down here. And as I keep doing it, it's going to keep building this up. Now, because of the way that they're selecting these, we're going to expect that we're going to have more being collected in the middle. And if I do this 1,000 times, I get this kind of a distribution. Now, this is not a bell curve. This is not a normal distribution. It's actually called a triangular distribution. And if I do it, several thousand times, we can see that we're actually going to get what looks like a pyramid or a triangle. But here's where it comes into play as far as the central limit theorem goes. I'm going to go over here and I'm going to change my sample size to 35. And now as I start doing some samples, here's 5 times, and I do it a sample of 30. So I'm picking 30 numbers from here, and then I do my 5 sample means from those 30. I'll do one of them here. So here's one, and then it picks all of these from here. So I'm picking 30 numbers from this population that I have up here, and I'm getting the mean of that. If I do this 1,000 times, 2,000 times, 3,000 times, we get the bell curve, which is great for us because once we know the bell curve, we know the equation that goes with it. We know the probability values that can go with it. We can use the normal probability calculator that we have built into StatCrunch to be able to assess probability values based upon certain numbers in this distribution. And here's the cool thing. I'm actually going to grab here and I'm going to click and hold, and I'm going to create some wicked funky distribution. Okay. And the whole point is that it does not matter what this distribution is. If I sample this thousands of times, I'm going to get an approximately normal distribution from the mean of those sample means. I could have completely inverted, doubly inverted. It doesn't matter. The means of those sample means are going to get this type of distribution. Now, if I change my sample size to something like 5, for example, and now I run the same population distribution that I have here, and I run it 3,000 times, I'm not going to get that normal distribution. Now, it's approximately normal. It's a little bit flat, and most of that is because these two dips are approximately the same. But if I had something that was completely skewed, okay, and I did this 1,000 times, this is not quite a normal distribution. You can see that it's skewed over here a little bit. It's pulled a little bit in the right direction. Now, let's say that I start with a normal distribution. So I'm going to pick a bell-shaped curve where I have a mean of 25 and a standard deviation of 5. Now, I could use whatever I want. Let's say I'm using body temperature, and I did 98.6, and I did a standard deviation of 0.6. That's relatively arbitrary what you're using it for. Here I'm going to get a nice bell curve, and I can see the values that I have here. I've got 98 and 99. I get 98.6 in the middle. Now, if I make my sample size, let's make it 5, for example, we know that we're not supposed to get a normal distribution. But if we start with that normal distribution and we do this 1,000 times, then we're going to get a normal distribution. So this is where we get to use something called the central limit theorem. Now, the central limit theorem is really just a derivation of what we're using for the normal distribution in our z-scores. What we do is anytime you have a sample where it's 2 or more, and you want to do the probability of the mean of something, and not just an individual value. You have values that are a sample of 2 or 3. Let's say you want to know what is the probability that the average weight of a group of 12 is greater than 180 pounds. That's great. We're going to use stat calculators normal for that. And let's ask that question. What's the probability that I have a group of 12 where their mean weight is greater than 180 pounds? Let's say that the mean weight of all men, for example, is 175 with a standard deviation of 35. And I want to know what is the probability that a single man has a weight greater than 180 pounds. In this example here, we can see that that probability is going to be 44%. If, however, I have a group, what I do is I modify my standard deviation and I divide by the square root of the size of the sample. So I'm going to put divide here, and then I'm going to type in the letters SQRT. And I had a group of 12, I think is what I was just saying. Now I'm going to put in divide by the square root of 12. I'm going to get a different probability. It's going to be less. And the reason why is because those means tend to have less variation. And so this square root part tells us that it's going to be less variation. One example I traditionally use in class is, let's say that we have a gondola, a ski gondola out in Vail, Colorado, for example. And let's say that ski gondola holds 2,000 pounds and you have 10 people get on that ski gondola in the morning. All right, so let's make the assumption that it's all guys, right? So, and the mean of those guys is 175. And let's say that the standard deviation for the weight is 35. Now, if on my calculator I take 2,000 and I divide that by 10, I'm going to get 200. Okay? That means that, let's say the average weight was greater than 200 for those 10 people. If that's true, And think about this. If their average weight is greater than 200 for all 10, then that gondola is going to exceed its weight capacity. If the average is 201, for example, and I take 201 and I multiply it by the 10 people, that's going to come out to be 2,010 pounds, which is going to exceed the capacity of the gondola. So here on StatCrunch, I'm going to change my standard deviation. I'm going to divide it by the square root. I type in SQRT, and in parentheses, I'm going to put 10 and hit compute. We can see that the probability that gondola is going to be overloaded is going to be just over 1%. So nothing too sketchy there, okay? But let's say that the gondola was rated for 12 people. If I change this to the square root of 12 instead of 10, I'm still asking the same question where the average weight is greater than 200 pounds. I go ahead and click compute, and that's going to be, wait, did I actually change it here? And let's say that instead of 10 people on that gondola, I'm going to change that to 12 people. I'm going to change this to 12 here, but then I also have to do 2,000 divided by 12. And that's going to be 167. Now when I calculate that probability, there's a 79% chance that that gondola is going to be overloaded just by adding 2 people onto that gondola. And so this is how the central limit theorem works. It works just like the normal distribution calculator, except that your sample size is going to be 2 or more, and you're going to use this normal distribution calculator that we used before. Again, central limit theorem, you can use it if your sample size is greater than 30, then it doesn't matter what your original population distribution is, or if your population is a normal distribution, this bell curve that we're looking at right here, then it doesn't matter what size your sample distribution is going to, your sample size is going to be. Okay? Thank you very much, and talk to you later.